I'm going to continue work on this ocean project, or this ocean chunk of the project we've been working on. I got some normals, but they're not very good. You can see here, they don't look great. So I'm going to be trying to fix that today. They're also not scaled properly, and they're just wrong. So today I'm trying to figure that out. So, I think I found some information. So I want to just find. I found this one. No, not this one. Kind of one. No, see, I found one a minute ago. Yes. I found one a minute ago when I was on the toilet. Um, these don't actually look that good. Now here, here's a block
Choose Optimal
diagram.
Mobile or pay the price. Switch and save up to 50% on your mobile bill versus Verizon.
So multiply that.
But I'm really looking for. This was the one. All right, here we go. This is what we want. So let's look at those nice shiny normals. let's just grab our existing function and paste it in here so we're sure we're working in the same context. Okay. So we're not going to do it like this anymore. Num waves. Okay. 3 accumulated normal. 3. Shouldn't need these. Alright, I think we're on the right track here. So this is our bare bones. Get the displacement only. We get rid of this. Um, Alright, beautiful. So now inside this loop, for each wave at each world position, we have some math here to do. Okay, float WI. Let's get all of this. Actually, let's go ahead and get I want to look at what this is compared to the Gerstner wave. Because we'll have to change this somewhat. Okay, this is the actual Gerstner calculation. Directions I dot x times WA times cosine of R. It's this part. Okay, let's give this to the coworker. Um, so I know that we should not be invoking wave function multiple times there in a discrete norms that does not require offsets, and it should also yield better results. Take a look at this implementation of flat non-spherical Gerst. Pay attention to calculates the normal contribution. There should be some way to alter this to work in our Alright, so this is just extraneous code here. Length, amp, speed. Okay. Alright, so let's just start implementing the things we need. So WI is equal to 2. Um, let's actually make another function here. Kirshner wave. 3. Kirshner. I equals two times pi divided by wavelength. Am I doing that in the material here? Because we should probably not. We're not. Float R equals WI times dot displaced position. 3 displaced position equals position plus displacement. WI times the dot product of the wave direction and the displaced position. is phi? Speed times wi plus time times wi plus. Oh, that I see. We don't have to do that. We're doing that externally. So we can just get rid of that. This is just our modified. Wait. Is this our phase? We'll just leave it for now. We're gonna have to fix all this anyway. Normal minus equals directions I times WA times cosine R. What was WA? Wave WI times amplitude. WA equals wave dot amplitude times WI. Normal minus equals dot direction times WA times cosine R. Steepness divided by amplitude times number of waves. That is the equation here. QI is equals QI times WA times sine of R. Then we can plus equals cursor normal, position, wave displacement, accumulated displacement, time, waves, I. I don't think this is going to work, but let's give it a shot. Okay, normal. Save it and take a look. Oh, didn't do it. This is great, but I want to adapt our existing code, not implement the code. Linked code. Here is my first pass, but it is wrong. Can you help me fix the normal function? Let's give this a shot. displacement, but I don't know how that's gonna work. Well, we do have some kind of normal-ish things going on here. Hey, now wait a second. That might actually be it. No, not quite. Shouldn't you have to take the displacement into account? Also, shouldn't we? While it's doing that, let's take a look at it. Three position plus displacement. And then right here, on pause. Anywhere else that we're using the position here? Don't see it. So displacement. Let's try that. I think we're definitely on the right track. But we're not there yet. We need to be scaling by the amplitude, like the contribution is too much. Let's find a deeper spot. Trying to find the deep end. Over here, maybe. Let's turn the amplitude up a smidge. And let's actually exaggerate it, right? It's not too bad, but it seems like there's too much contribution from the like smaller wavelengths, I think. But it's getting there. Too close to the surface here. Uh, how about over here? Here we go. Now we got some thick waves. Too thick, but good for our purposes. Yeah, this is definitely not exactly right. Let's also unflatten the normal so that we can really have a good look at what we're working with here. Maybe it is correct. It doesn't actually look wrong. I think our accumulation method is probably wrong. It was using minus. Hang on. Okay, first of all, So this is a 0. Wait, this is, hang on, in here. Oh boy. Okay. Shouldn't this be a minus? Maybe, maybe not. See what happens. And then next, this be 1, 1, maybe? If I do pluses here, what happens? Just out of curiosity. It's definitely closer. It's the inverted. Yeah, so it's minus. Is it really minus plus? That seems wrong to me. In the paper it was minus minus. That's it. I think that's correct. Like, look at the surface here. We have nice normals. Now, what if I do this? Seems to be the same. I definitely think we're on the right track. Doesn't seem to make a huge difference either way, right? This might just be it. Let's see. Does this method take into account the reduced contribution from lower levels of amplitude? Because I think our biggest problem is that we have like equal contribution from our high levels of amplitude and our lowest levels of amplitude. We could probably just hack it like this. Normal equals times plus, okay, we'll do this. Float 3 norm wave norm equals wave norm times equals waves I amplitude wave norm, something like that. Aha! Ha, 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 ha. And obviously it's too much, but I think that might have cracked it. Oh, gonna sneeze. Mm, excuse me. Okay. Bu- 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 bu. Those are looking much better. Except here. I think we're gonna want to pass in the depth, probably, but let's for here, let's just try this divided by 1,000. Just for the time being. Divided by 10,000. This is 0, 2. I don't think we can have any like baseline assumptions here because we're doing it in 3 dimensions instead of two. So like fundamentally we're doing a different thing here than let's flatten that normal a bit. 0.75. Starting to look pretty good. Point 0.8, 0.9. And then the other thing we can do is we can probably get rid of like the lower half of our iterations as far as calculating the actual offsets and only calculate normals with them because we don't need like micro displacements in our mesh, right? We just need the big blocky wave shapes. So can't do this like that anyway. Okay, now in our initialized waves, we'll say we'll bring back the concept of int octaves 0, octaves plus plus, and then wave octaves less than 4. So for the first 3 octaves, we'll do that. Flagged as true, and then for the last we will not. And then here, if waves I dot normal only it's not a normal only, we will increment our accumulated displacement. Otherwise, we will just calculate the normal. Okay, it worked. It at least builds. Save it. Listen over here and take a look. There it is. Let's kind of unflatten it a bit and see how that works out. Daddy, hush up, you fool. Seems reasonable. Except, is it just me, or where's my light source? There it is. I don't think it's quite correctly oriented. But at the very least, we have something resembling correct normals here. Oops. Point 0.8. 5, 9, 85. Alright, and now what happens if I remove the amplitude scaling? Yeah, you need the amplitude scaling. Maybe we could reduce it. Yeah, we give it some baseline amount here. And then the more we divide this by, the bigger it is. I'm going to incorporate the depth into this function as well, so that I don't have to worry about like multiplying it externally or anything like that. And now another cool thing we can do with this, we can create more octaves. So we go to 5 and then change our threshold here to 5. Okay, too much. A little too much, I think. How many waves are we at? 60. Let's do 6. And then let's have our. With 6, we would have 10 octaves. But we're only going to calculate normal for the last 6 of them. We're not going to do all sets. Decrease the lower level contribution factor. Decrease it again. Alright, what else is divisible by 60? Teddy, hush up, fool. So at 6, at 10 we only get 6 octaves, so this is actually only doing the last 2. So I think here we'll do 3. That's going to take waves out. Let's try 2. It also probably makes it faster because we're not having to do as many calculations. And we're close, but we're still compositing them wrong somehow. I'll have to figure that out. Actually need to take that little pup out on his walks here in just a minute though. We're definitely closer than we were. Hey, buddy, you want to go outside? You want to go on a walk? You want to go on walkies? Is that what you want? Is that what you want? You want to go on the walkies? Oh, oh, yes, yes, Dad, please. Please take me on the walkies. Please take me outside. I really want to go. All right, I'm gonna take this guy on his walk. Um, Later.